It's given us new opportunity, new hope, and it depends, of course, how it's used.
Well, bearing in mind Britain's present balance of payments situation, one must ask, where would we have been without it?
I think it's given people a lot of employment.
Well, it's keeping us afloat, really.
In 1967, we had 1 helicopter, 30 staff, and 4 flights a week. And now we have 23 helicopters, 400 staff, 60 flights a day. The growth rate has been tremendous.
I see it as a stepping stone to greater prosperity.
Well, I would say it's really got us out of a hell of a mess.
It's 1978, almost 20 years since we first asked, is there oil and gas under the North Sea? 14 years since the first exploration well was sunk. The whole story is one of pioneering, dedication, high risk and high adventure. It's also a tale of success for the country, for every one of us. For Esso, the crown of that achievement is Brent. So let's look at the story of Brent, a system for success.
You could say that it first began in 1888, when Esso first set up shop in this country as Anglo-American Oil. Queen Victoria was on the throne. The oil was for lamps to light your house. But the actual North Sea involvement started in 1959. The first section of the M1 had just opened. It was that long ago. In the Netherlands, a company owned jointly by Esso and Shell discovered a huge gas field at Groningen. The same geological features stretched out under the southern North Sea. Was there gas there too?
1964, the year of the Tokyo Olympics. Esso and Shell set up a joint venture to search for oil and gas in the British sector of the North Sea, with Shell as the operator. One exploration well was drilled 140 miles off Sunderland in 75 feet of water.
1966. Francis Chichester began the first single-handed voyage round the world. Esso's first North Sea gas discovery. The Lemon field in the southern gas basin, still one of the largest offshore producers in the world.
1967. Something happened to British television. Color transmissions began on July 1st. More gas found in the Indefatigable field, and the first North Sea gas came ashore.
1968. We were talking about Apollo 11. Next year, Neil Armstrong would take his giant step for mankind on the moon. Lemon came into production.
1971. Decimal currency was introduced in the UK, and the Auk field gave Esso its first North Sea oil find.
1972. Iceland extended her fishing boundaries to 50 miles, and the Cod War was on its way. Brent, the biggest field to date, declared commercial. Then Cormorant. Then the first well west of the Shetlands was drilled.
1973, the year that oil prices rocketed. Black gold suddenly seemed less of a cliche as North Sea oil took on a new and even greater importance. Another oil field was discovered and named Dunlin.
1975, the Common Market referendum. Construction began on the pipeline from the Shetlands to the Brent area. The Brent B platform was placed.
1976, the first supersonic passenger flight as Concorde came into service. Brent D and Brent A were placed on the field. Spar, the unique floating terminal, was floated out, and a North Sea landmark, the first oil was brought ashore by tanker from Auk in February and Brent in December.
1977, the year of Her Majesty Queen Elizabeth II's Silver Jubilee. Esso celebrated with oil confirmed in the Fulmar field. The Brent D platform began production. A third production platform was set on the Indefatigable field, and CMAC-1, the world's most advanced pipe-laying vessel, was at work on the Flags gas line.
1978, the first radio broadcasts of Parliament. The Flags line was completed 2 months ahead of schedule. Dunlin produced its first oil in August. Brent C was placed. 375,000 metric tons of Cormorant A floated out to complete the Brent system. Then, on November 25th, the first oil ashore through the Brent pipeline arrived at Sullom Voe from Dunlin via Cormorant A. Esso had spent £360 million in this year alone, an indication of the enormous scale of the commitment of money and resources to the North Sea venture.
That is a thumbnail sketch of the biggest offshore oil undertaking in history. Sounds easy when you say it. You discover an oil field, you set a platform, you lay a pipeline. Let's look at the reality. The early 1960s, mineral rights had been assigned in the North Sea by international treaty. The British government divided its sector into blocks of about 100 square miles, then allocated them under license to suitable applicants. So, how do you find an oil field? Ask an exploration manager.
In 1964, Esso and Shell pooled their money, technology and expertise, realizing that working together was the best way of meeting the mind-boggling challenge of exploration and development in the toughest conditions the oil industry had ever tackled. Initial exploration using marine seismographs, magnetic measurements and many other techniques will tell us whether or not an area might contain oil-bearing rock. If the signs are hopeful, we'll do more detailed surveys. And then exploration or wildcat wells will be drilled to try to find the oil. Unfortunately, most of these wells don't find commercial deposits. From nearly 800 exploration and appraisal wells drilled in the North Sea, only 22 fields have so far been discovered. And that's a measure of the immense amount of technological effort, money, and dedication that's gone into this high-risk gamble by the oil companies. Without this willingness to pioneer and adventure, we'd still be looking for oil instead of producing it, with all the benefits to the country's balance of payments and security of supply. Once a wildcat strike looks promising, appraisal wells are drilled. These will add to the wildcat's information about the thickness of the strata, the reservoir characteristics, anticipated production rates of oil and gas, and whether it's likely to be a commercial proposition. At the same time, the best method of carrying the oil ashore will be studied.
To date, the Esso Shell partnership has discovered 1/4 of all the oil and gas found in the North Sea. But what do you need to drill your hole in the seabed?
This is a typical exploration vessel, Ocean Voyager, a semi-submersible drilling rig working here on the Fulmar field. Semi-submersibles are the most stable vessels for drilling in rough seas. They're mounted on large pontoons floating below the surface and anchored over the selected site. Another possibility for deep, rough water work is the drill ship. This carries its equipment amidships, lowering the drill string through the bottom and keeping position either by anchors or the use of thrusters. For calmer, shallower waters, there's the jack-up rig. This lowers its legs to stand on the seabed, forming a temporary platform. The technology of exploration had to be revolutionized for the North Sea. Even giant concerns like the Exxon Corporation, Esso's parent company, with many years of offshore drilling, had little experience in these conditions. Most of their work had been done in the relatively mild and shallow waters of the Gulf of Mexico. For the giant waves, murderous winds, and great depths of the northern North Sea, completely new equipment was called for. And the cost? A semi-submersible cost around £25 million to buy. Each well it drills costs £2 million to £5 million, and its running costs while drilling are about £45,000 a day. Even when it's not working, it's costing up to £15,000 a day to run. Bear in mind that it may be several years from the drilling of the first wildcat well to the final appraisal well, and the sum involved is almost too large to grasp.
And this is only the stage when it's possible to say, yes, there's oil. Now we can think about getting it out from under the seabed. The first thing is to obtain government permission to go ahead. Then, what's involved in production? Listen to two production managers.
At the top of the list comes the huge capital expenditure of building and placing the hardware for production. Look at the Brent field. It's a vast reservoir of oil and gas needing 4 platforms to handle it, big enough to justify a pipeline to shore. This is the Brent area. Brent Dunlin, Thistle and Murchison will pipe their output to the Cormorant A platform, which, besides collecting and acting as a production facility for its own field, pumps the oil ashore to Sullom Voe in the Shetlands. The gas goes to St. Fergus. The Brent system consists of the collection and pumping facilities on Cormorant A, the pipeline itself, and the terminal at Sullom Voe. That alone is an investment of over £2,400 million. It's also an excellent example of the industry's ability and willingness to cooperate for the common good. In 1974, 17 oil companies joined together to build it, 70% of that involvement being Esso shells. The eventual cost of the whole Brent area complex, including all the gas and oil pipelines, will be about £3.5 billion. Now, about the platforms.
A platform's job is to provide a safe working area for all the operations involved in getting the oil and gas out of the reservoir and on its way to shore. It's also home for the men who operate the equipment. There are two main types of platform in the North Sea, steel or concrete.
The steel platform stands on hollow steel legs which are pinned to the seabed by piles. It's a well-tried design, commonly used here and overseas. The jacket, the legs to support the deck, is built on its side on shore. This is Brent A under construction at Methil in Fife in 1975. The platform is enormous, weighing 14,000 metric tons and designed to stand in 460 feet of water. That's 100 feet more than the height of St. Paul's. It also has to withstand the possibility of 100-foot waves and winds up to 125 miles an hour. Remember, the Brent field is in the same latitude as Alaska. Normally, a steel jacket is floated out to the field on a barge or a huge detachable raft. Brent A was too big for this, so the structure itself was made to float. In May 1976, it began its 4-day, 400-mile journey to the Brent field. May 15th, on site and ready for setting. To ballast and upend it, the compartments in the legs could be flooded individually at the touch of a button on the remote control system. This meant we could stop at any time, adjust the position of the jacket, then continue setting within really accurate limits. The next job was to pile the jacket in place. That's what takes the time, especially if the weather fails. Another costly and complicated piece of offshore hardware, the crane barge Odin, took his giant 300-ton hammer in his hand to do this. Next, the deck had to be shipped out and lifted into place, ready to receive the modules containing the platform's technical equipment and living quarters, which Odin placed during the following season.
The concrete platform, by contrast, can be almost fully equipped on shore, then floated out to sit firmly on the bottom through its own weight. The onshore costs can be higher than for the steel platform, but this may be offset by the need for much less work on site and its ability to get into production faster. It also has its own storage capability. Various factors dictate the choice of steel or concrete. The need for offshore storage, the composition of the seabed, and so on. Ultimately, it's simply a question of which is the best. On the Brent field, for instance, A is steel, while B, C, and D. This is Brent B, weighing 348,000 tons. It's 813 feet high, 200 feet taller than the post office tower, with a 300-foot diameter base providing storage for almost 1.25 million barrels of oil. The cost? £150 million for the platform, including processing facilities. If you add in the cost of its associated wells, pipelines, and compression equipment, the price goes up to between £300 million and £500 million per platform. The cost would be even higher if construction were undertaken today. On August the 4th, 1975, Brent B began the journey out to the field.
August the 10th, and the platform was in position. The first on the field and preparing to produce its first oil in December the following year.
The largest platform in the Brent area is Cormorant A, the key element in the whole complex, collecting, producing, and pumping. Cormorant A is another variation on the concrete theme, built at Ardine Point in Scotland. She and her slightly smaller counterpart, Brent C, gave employment to a workforce of 2,400. Cormorant A was set on the field in the summer of 1978.
So, the platform has been set. Now we have to drill wells, up to 40 for each platform. The wells curve outwards so that they can drain as wide an area of the reservoir as possible. Bear in mind each platform's cost, and you'll understand why it must be used to the absolute limits of efficiency. The number and spacing of the wells is critical.
The high cost of each well makes it undesirable to have too many. But if you have too few, there's the chance of leaving oil behind. So the optimum distribution has to be carefully engineered. Having drilled its wells, the platform now has other jobs to do. It has to separate and compress the gas from the field, either to send it to the mainland, or, as with Brent B, to re-inject it into the reservoir until the pipeline to take it is ready.
And that brings us to the next major problem in the production cycle. Collecting oil from deep down under the seabed is hard enough. But how do you get it ashore?
There are two main choices, tanker or pipeline. Initially, tankers are cheaper. So if a field is too small to justify the huge cost of a pipeline, that's the answer. Ork is a case in point, producing through an ELSBM, an exposed location single buoy mooring. Crude is piped from the platform through a seabed pipeline, feeding the tanker through hoses mounted on a turntable. This means that it can swing through a full circle, aligning itself to the prevailing wind and current, and always remaining head-on to the weather. It's safe to use this method up to a 16-foot wave height and a sustained 20-mile-per-hour wind. However, even with a constant stream of tankers, there must be interruptions in the oil flow if we have no storage. But let's look at Spar. It does the same job as the ELSBM, loading tankers in the middle of the sea. It's also a mini terminal and floating storage tank, holding 300,000 barrels of oil. Whilst the ELSBM is unmanned, Spar has living quarters for a crew of 12 to 15. There are diving facilities with a bell lowered through its center column and a built-in decompression chamber. It's 400 feet high, with the top 150 feet above the waterline. It can take oil from the platform and feed it to a tanker at the rate of 250,000 barrels a day. In the summer of 1976, Spar was towed out and anchored near Brent B to get oil production started while the pipeline was being completed. By the end of the year, the first oil from the Brent field had passed through it and been landed at Fawley by the Esso Warwickshire. Spar, another example of the original and inventive thinking to solve the problems the oil industry was encountering at the frontiers of offshore technology. Given a really big field, the cheapest way to get the oil ashore may be through a pipeline. But the potential must be vast to justify the enormous expense. Let's take the Brent pipeline, the world's deepest large diameter line. It cost £1 million a mile. That's the same as a mile of 6-lane motorway, or 5 miles equals the cost of building a modern hospital. It's 93 miles long. How is it laid?
It's done by a lay barge, a floating factory for welding the lengths of pipe together and laying it on the seabed. It has a crew of around 200 and costs about £50 million. The welding cycle takes between 12 and 15 minutes. Then the barge moves forward 40 feet on its anchors, feeding the pipe down the stinger into the sea, and the whole process is repeated. A survey using every technological aid possible determines the best route for the pipeline, and this must be followed precisely. The lay barge triangulates its position with 2 shore-based Decca trisponders, a pattern duplicated by teleurometers of the same positions. Astern, Vickers Venturer does the same. She also knows her position relative to ATNAV buoys on the seabed. Pisces 3 checks her position by Venturer and the ATNAV buoys. MV Asilla brings up the rear. As well as using the shore-based signals, she checks that she's precisely over the pipe by echo sounder. This double and treble checking means that the barge can be positioned within 2 meters of the chosen route.
FLAGS is an acronym for the Far North Liquids and Gas System. At 280 miles, the North Sea's longest pipeline. It's the vital artery for bringing the Brent gas ashore to St. Fergus. Vital because by 1980, gas will be supplying 23% of our total energy needs. Let's hear about the shore terminals.
At St. Fergus, methane will be extracted from the gas for delivery to the British Gas Corporation. The plant is designed to receive 1.1 billion cubic feet of gas a day through the FLAGS line and is landscaped to intrude as little as possible. Similarly, an enormous amount of thought and money has gone into minimizing the impact of the huge Sullomvo terminal in the Shetlands. This, the oil terminal for the Brent area and the other fields of the East Shetland Basin, will be one of the biggest in the world. By the early 1980s, it will be receiving 100 metric tons a year through the Brent and Ninian pipelines. Eventually, it will take almost 2/3 of all the North Sea's oil production. There's room for giant tankers capable of lifting up to 300,000 tons of crude. The tanker jetties and harbour have been built by the Shetland Islands Council, who operate the port in management partnership with the oil companies. They'll receive an income from the oil companies of £100 million by the end of the century. Work began in this remote and beautiful corner of the British Isles in 1975. And in December 1978, the first tanker load of oil went on its way.
How long will the oil last?
The latest government estimates of proven, probable and possible reserves are between 2.4 and 4.4 billion metric tons. Very roughly, the average life of a North Sea field is around 20 years. But as production is staggered, the overall period will be somewhat longer. Next, safety and pollution. Two topics which the oil companies keep constantly at the top of the list. Our two experts again.
Getting oil from under the sea must be carefully planned. So the Petroleum Industries Training Board run courses and programs to make sure that all personnel are fully aware of safety rules and procedures. Dundee, firefighting. Fort William, diving. Aberdeen Airport, helicopter ditching. Aberdeen, survival at sea. Each platform has its own lifeboats and can call on helicopters for emergency evacuation, as well as a workboat standing by at all times. The platform itself has to have a government certificate of fitness to operate, renewable every 5 years, while government engineers carry out spot inspections.
A potential danger of which the oil companies are very conscious is pollution. The first and most important line of defense is prevention. That means well-trained personnel, good equipment design, and meticulous operating procedures. Automatic shut-off valves and devices to warn of abnormal variations in pressure minimize the chances of pollution. If there is a spill, the platform's standby boat applies immediate first aid. If it's a more serious problem, there are troubleshooting facilities ready to move into action very swiftly indeed. The UK Offshore Operators Association keeps stocks of equipment and dispersants at strategic points to deal with any slick which should drift towards the coast, while the industry has a constant research program to produce even more effective methods and materials.
Now let's talk about money. The scope of the North Sea operation is vast, the costs enormous. Here, as simply as possible, are some of those costs so far. And remember, this is just Esso's half of the Esso Shell venture.
For the years 1962 to 1965, this is what happened. First UK license awarded. First exploration in southern gas basin. 2 exploration wells drilled. This is what it cost Esso. An average of 0.6 million a year.
1966 to 1969, 28 exploration wells drilled. Exploration in central North Sea. Southern gas fields discovered, developed, and production started. Cost 7 million a year average.
1970 to 1973, exploration northeast of Shetland. Auk, Brent, Cormorant, and Dunlin discovered. Development begun. 35 exploration wells drilled. That cost a yearly average of £20 million.
1974 to 1977, oil pipeline laid to Sullom Voe. Intensive development and production start-up at Ork and Brent fields. Fulmer field discovered. 56 exploration wells drilled. Average yearly cost £216 million.
1978, production start-up at Brent A and Dunlin platform. Gas pipeline laid to St. Fergus. First oil shipment from Sullom Voe. 14 exploration wells drilled. Expenditure for this 1 year, £360 million.
To complete the development of existing projects will take another 3 years. So let's add that to the costs at an average of £400 million per year.
Total costs jumped from 110 million at the end of 1973 to almost 1,000 million 4 years later, and 1,300 million by the end of 78. By 1981, it will be 2,500 million pounds.
And that is just Esso's contribution. It's worth repeating that this virtually is the cost of the Brent field alone, without allowing for operating and maintenance. Add in the gas and oil pipelines and the facilities for the whole Brent area, and the cost for just that one element of the North Sea province is £3.5 billion. By 1982, the total industry in the UK sector of the North Sea will have invested a total of £20 billion. That is equal to 2 years of Britain's whole capital expenditure. Government, private industry, local authorities, the lot. Getting oil from deeper, stormier, colder waters becomes costlier, more difficult. First, it was short steel platforms, then tall steel platforms, followed by tall concrete platforms. What next?
Subsea completion is a major development, finishing off the whole well on the seabed. A series of wells are drilled separately in widely spaced locations. Then, seabed pipelines join them all to a common collecting point. This is already in use as an extension of some platforms, where the field is too big for one, but doesn't warrant the expense of two. The more advanced version of this is the underwater manifold center. It does the same job, but has a built-in remote control overhaul system to change valves and do regular maintenance, all from a ship on the surface. The oil can be loaded from an offshore mooring point, just as with a conventional platform. As it's on the seabed, the underwater manifold center avoids the battering of waves and strong currents.
That's for the near future. But where have we got to now? It's almost 20 years since that gas find in Holland started the whole North Sea saga. 14 since the first exploration well was drilled.
Esso has been and continues to be a major supplier of gas to the UK from the southern North Sea. We've been a 50% partner in the finding of oil, the developing of a vast oil province, and the building of the complex infrastructure of recovering that oil. Again, we are a major supplier of the UK's needs. The oil industry provides employment for some 14,000 people offshore. Currently, there are around 85,000 employed on land in oil-related jobs. There are other, wider benefits. 1, security of supply. We are less dependent on outside sources than any other European country. 2, the benefit to the country's balance of payments. Until 1973, it was reasonably good. But in that year, the rocketing price of oil put every developed country in the world well into the red. North Sea oil was the critical factor in improving the situation much faster than we had any right to hope. And 3, the huge revenue accruing to the government. Special taxes and royalties mean that they take by far the larger proportion of the revenue. In every way, North Sea oil has been very good for Britain.
For the participating companies, the commitment in terms of money, manpower, expertise and dedication has been enormous. The result, a tremendous success story. Up to date, the return on the investment has been very limited. Now it's just beginning to pay off. And pay off it must, for two powerful reasons. The first is that there will be a reluctance to invest in the increasingly risky business of developing the smaller fields unless there is an appropriate return. Secondly, as the demand for oil increases, finding and getting it from deeper waters, from even harsher environments, will need unprecedented capital investment. That will not be available without sufficient incentive. So, at the end of this beginning, as Britain reaps the benefits of this new and different harvest from the North Sea, what are the tasks for Esso during the next few years?
We must finish development of the complex oil production and gas gathering projects that we've got underway. We must ensure the production of more than 15 million tons of oil a year by the middle 1980s. We must carry on a major exploration and production program at a cost of £400 million a year upwards to meet that requirement. This vast, adventurous project has been a story of success for Esso and for the country. Our future commitment must be equally intense, then given a clear energy policy and a stable investment environment to support the confidence of the industry, that success will continue.